In this example, we're going to explore the limitation of d2y dx squared as a method of distinguishing between types of turning point. If we consider y equals x cubed, to find the turning point, we do dy dx in the normal way. We get 3x squared. We need dy dx to be equal to 0, so 3x squared is equal to 0, and this tells me that x is equal to 0. If x is equal to 0, substituting back in, we find y is 0, so our turning point is at 0, 0. If we differentiate again to find d2y dx squared, we get 6x. When x is equal to 0, d2y dx squared is 6 times 0, which is 0. If we now consider y equals x to the 4, differentiating gives us 4x cubed, and setting this equal to 0 to locate the turning point gives 4x cubed equals 0, so x is equal to 0. Substituting into the original y equation gives us 0, 0 as our turning point. Differentiating again, d2y dx squared would be equal to 12x squared. And when x is equal to 0, d2y dx squared is equal to 0. If we now consider y equals minus x to the 4, dy dx will be minus 4x cubed. So minus 4x cubed is equal to 0 to locate the turning point. This tells me x is 0. Substituting into the original equation gives y is 0, so our turning point is at 0, 0. d2y dx squared is equal to minus 12x squared, and when x is equal to 0, d2y dx squared is equal to 0. So all three of these gave d2y dx squared as equal to 0. Y equals x cubed actually has a horizontal point of inflection. Y is x to the 4 has a minimum, and minus x to the 4 has a maximum. So we can see that d2y dx squared being equal to 0 tells us nothing, since we've produced 0 in all three cases, and yet we have one horizontal point of inflection, one minimum, and one maximum. So to repeat the rule for d2y dx squared, if it evaluates to a positive number, we get a minimum. If it evaluates to a negative number, we get a maximum. But for d2y dx squared equals 0, we cannot tell. It could be any of the types of turning point, so you should use a sign table.